Well, why don't we go ahead and I guess start up a little bit here. I've got about 4 or 5 after here, so people can. Hank, if you just kind of keep an eye out if people start to join us
the
late.
waiting room, right?
I appreciate it. So I'd like to welcome everybody this evening. My name is Joel Kirshen. I'm president of the St. Louis CSI chapter. I'd like to welcome everybody to our continuing education session tonight. The session tonight is sponsored by Pella, and the presenter is George Ramsay. George is a longtime member of CSI. He's been the past president of the Minneapolis chapter, and he's going to hopefully make some of these, make some of this a little simpler for the for those of us who have issues with, Greek letters and forms. I did want to bring up that the AIA credits are going to be coming through Pella. If you have, we're going to be submitting all the information based on those who have registered through our site. If you happen to be joining us and you didn't register, if you pass on your email via the chat link, we can gather that information. And I guess remembering the right process, if you need AIA credits, go ahead and pass on your AIA member information via the chat link, and we'll compile that and get that in. Credits will be distributed, just certificates, let me rephrase that. Those who want certificates, those will be coming through Pella. So yeah, in your chat, let us know that too. I did want to bring up one other thing. We're trying to continue to keep some interest and activity and help on our site. So if you have some blogs that are of a more, addressing certain technical issues that you've run into, or you have a product that addresses certain technical issues, we'd love to hear from you. So you can send your information to Steve Gantner, and Steve just included his email in your chat box. And Steve, we can, use Steve as our clearinghouse for things, and but we're always looking for content to post out to our website for everybody. Okay, enough me. Let me turn this over to George and let him get going. George, thank you. Go ahead.
Thank you, Joel. Thanks for joining, everybody. Nice to be with you. I live up in Minneapolis, as Joel said, longtime member since 2004 with CSI. I was past president, president of CSI Minneapolis St. Paul in 2016 and 2017. Went on to do regional work, actually worked with Steve Gantner on some projects, and that's a real privilege to be with you tonight. So what you're looking at right now is just a little worksheet that George Everding had sent out to everybody. If you want to print it out and follow along, it just makes it a little bit more engaging, or if you just want to write down these little characters, and even especially at the top is what we're really going to start filling in, just makes it a little bit more engaging, a little bit more, something to do. And don't let this bother you, because this is my goal tonight, is at the end of this is all going to make sense, believe it or not. So it is engineering, but it doesn't get too in depth. And like we were discussing a little bit earlier, there's not a lot of math. And the reason that we do it longhand like this is just so you understand the concepts. And then I will show you a tool. There's a calculator that you put all this information in and hit enter, and boom, you get what we're looking for at the end. So the key is just understanding, especially those top categories, on the information that you really do need to get your design pressure and then your performance grade, and then ultimately how to spec windows and doors based on performance. Right, and as mentioned, we are given AIA credits. Just get your AIA numbers into the chat, and we'll make sure we get those out. And then if you do want a certificate, we'll definitely get those out per your request also. So we're really going to look at determining design pressure and then make some calculations based on some building sizes and locations. And then we're going to understand the differences between design pressure, performance class, and performance grade. These get commonly confused. So that's the other goal, is to make sense out of the differences in those concepts. So when it comes to performance, windows and doors, fenestration, it makes up all these different bullet points. So air, water, structural, thermal, all this stuff. This is all part of performance grade. And really where it starts is air, water, and structural performance. So just to make it as easy as possible, we're just going to boil it down to air, water, and structural as being the basis of this presentation. I will touch slightly on the rest of this, but it's mostly going to be on air, water, and structure. So the biggest thing here is one of the most common questions I get from architects is to, and spec writers, is to make them understand the difference between DP and PG. So DP, design pressure, is a site-specific measurement. So we'll put in the actual address of that project just to get what the average wind speed is. So a good way to look at that is Miami versus St. Louis, two very different areas when it comes to hurricanes. St. Louis isn't in the tornado alley. So just think of design pressure as being the basis of our calculations, and it really does come down to where that project is. Performance grade utilizes design pressure in that calculation, but there's all these other things that go into PG, performance grade, and that includes all of this stuff. So DP is part of PG. When you go to specify windows, we'll use PG, performance grade. And I just want to touch base on this, and then as we go through this process at the end, you're going to really get a lot better understanding of the differences in DP and PG. So then the other thing is performance class. And when you see window designations and specifications, a lot of times you see, CR50. So that's just a sample of the product type C, which here in the middle you see C is a casement. R is the performance class, which over here is kind of broken down by a gateway entry test. So years ago, there was actually 5 performance classes, and it was related to being residential, light commercial, architect windows. Now it's more just based on these basic tests for the gateway minimum performance requirements. It is not a code. It's not a regulation. It's nothing that you really have to worry about. It's just when you sit down at the very beginning of the project, you just want to think about what kind of project it is. So R, you can see that it's just a minimum gateway. So residential, light commercial can be residential, but then you're getting up to a little bit higher performance, and then your commercial, and then your AW. So AW is the granddaddy of all performance. So that's where you're seeing in your high-rise windows. That has to meet an AW requirement. And at the end, I'm going to touch on why AW is in a pretty much a separate class. It has a lot higher requirements in addition to this gateway test. So let's start off with wind pressure on a building and how that affects these calculations. So it's not just wind speed, it's location, it's the exposure of the wind, the building height, location of the windows, the size of the openings, the type of the building, and occupancy. So reference documents, this all springs from IBC, the Society of Civil Engineers, where they talk specifically about this wind load provision of AIA CES dash, I think it's even 12 or 16 now. The AMA WDMA CSA 101 or NAFS 101, we call it. That's our Bible, as part of the fenestration industry. That really lays out everything that we have to hit, the testing requirements and all these codes and standards. And then we're all going to put it into how to specify performance for windows and doors using all this information. So the IBC states that design professionals are responsible for determining wind pressure. So the engineers are going to do these calculations. As a window company.
Bruce, it's on. It's on. Bruce, it's on.
Can everybody put it on mute, please? Thank you. So we're always going to look at the structural engineers as giving us the ultimate wind loads that we're going to hit, but window companies will verify this. There's a couple of things I'm going to get into that not all engineers take into account. There's some deductions that some engineers and architects are fine with, but other engineers will say, no, we're not taking any deductions. So I'll get into that a little bit more. So let's go into the ASCE 7-10 for DEP requirements. So there's 3 different methods, and for simplicity's sake, we're just going to deal with the simplified procedure. As projects get more complex, you can go into analytical procedures and then wind tunnel testing, which is actual lab testing for really tricky installations. So we're going to have a case study, and this is One Southdale Place. It's up here in Edina, Minnesota, a suburb of Minneapolis. There's actually 3 buildings. There's a 10-story, a 5-story, and a 3-story. So it gives us a couple of different heights to look at. So for simplicity's sake on this one too, we're just going to look at the building C, which is the 3-story, about 33 feet high. Building B, 5 stories, was at 55 feet high, and then building A was 10 stories, and that was at 107 feet high. So once again, if you want to follow along on your worksheet, if you guys joined us a little late, try and jot these down. It just makes it a little bit more engaging, as I mentioned. So I'll give you a couple seconds here. It's in particularly just these across the top is what's important. Risk category, wind speed, exposure category, topographic factor, PNet 30, lambda, and then your design pressure. All right, ready? So there's 6 steps to determining wind load. All right. The first one, we're going to determine the risk category. And that is based on what is the end use of our building. So when we think about what that end use is, risk category 1 is a pretty simple building, a structure, barns and shelters, low risk to human life, and pretty simple, pretty basic. As we go up to risk category 2, it's going to be 1 and 2 family dwellings, multifamily, and office buildings, and then all other buildings and structures, not 1, 3, or 4. Okay, and then 3, theaters, lecture halls, schools, water treatment plants. So now you're seeing that this risk category, it's talking to about how many people are in there, if there is failure due to wind or storms, that it's going to impact how that building functions. So risk category 4 is hospitals, fire stations, emergency shelters, buildings with extremely hazardous materials. So failure of these buildings would pose substantial hazard to the community. So when you talk about risk category 4, this is the highest level, and it really does call for a lot higher performing products. So in our instance with Southdale being a multifamily, what would our risk category be? If you said 2, you're correct. And then that would go along the top of that worksheet. All right, so now we're going to determine the basic wind speed for that risk category. How do we do that? So wind speed is contingent upon the risk category location of the building and what type of building it is. So let's look at determining the wind speed, 1, 2, 3, or 4. We're also looking at higher levels of wind. And the way we do this is by looking at a map, all right? And so this was a basic map from years ago. So this is all on a website I'll get to in a minute here. But you can see most of the country is going to be at this 115 miles per hour wind speed. And then I think it's not 51 knots. I can't remember what the 51 is. But what's important to recognize here is you go down into Texas and along the hurricane zones, you're looking at these ultimate wind speeds of 180 miles an hour down around the Keys and up into Miami at 170, and then even up into the Carolinas. There's also differences of wind speed in some of the mountains. So the Adirondacks, down into the Smoky Mountains, the Rocky Mountains, of course, but most of the country is going to be at 115 miles an hour, including St. Louis and Minneapolis. So now following along on your worksheet at the top, we have risk category 2. Our wind speed is going to be 115 miles per hour based on our chart. But then let's ask, what if our building was a hospital? What happens? That means that they add a little bit more of a higher required wind load to meet. So it goes up 100 to 120 miles an hour in the Midwest, but you're seeing now down in the Keys and Miami, it goes from 180 miles an hour to 200 miles per hour. So this really impacts the hurricane zones. So as most of you know, it just takes a lot higher performing materials for those areas, but it does impact the Midwest slightly. So then let's ask another question. What if our building was a hospital in South Carolina? What's that going to do? So we're down here in South Carolina. Before it was at 150 miles per hour. Now we're at 160 miles per hour. So there's a 10 mile per hour difference, which doesn't seem like much, but it really does have an impact on things. I got called out once in identifying an assisted living. I was looking at it as a multi-family when actually assisted living counts as medical. So it did impact that risk category, and we had to increase what was required for the windows. So sometimes there's little things that you have to keep in mind. Like I said, the engineer is always going to help you, and then our architects and engineers, your window supplier company, will also run these calcs too. So this is the tool site. So instead of looking at that old chart, this is a pretty neat website to go to. So it's ATZ hazards by location, and you simply put in the address. So I'll just put in St. Louis here. And it brings up the elevation. And then based on 7-16 at that risk category 2 or 3, we're at 106 or 114. And you guys still might be on 710. So we're at 115 miles per hour for that risk category 2. So just keep in mind, hazards@council.org, pretty neat website. Okay, so wind load parameters now. How are we going to do this? That's based on what is going on as far as exposure. So now we're thinking about how wind is coming across the land by our project. So I'm looking at this Chicagoland area. It's by Lake Michigan. It's a huge downtown with lots of high rises. There's some airports. There's a lot of residential area. So each one of these different areas can impact another one of our criteria. So down here at Navy Pier, it's right by Lake Michigan. So this is going to be exposure D, and that is because it's so close to an open body of water. And it gets kind of complicated here, so pardon me for reading it, but exposure D is for buildings located along flat, unobstructed areas and water surfaces outside hurricane-prone regions, e.g. inland waterways, the Great Lakes, and West Coast shoreline, as well as smooth mud flats, salt flats, and unbroken ice. It also includes hurricane regions too. So keep that in mind. B, so B now, it's for urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstructions, having the size of single-family dwellings or larger. It's also upwind direction of at least 2,600 feet or 20 times the height of the building. So once again, it gets a little bit more complicated, but just keep B in mind as being for an urban or suburban area, okay? And then C applies in all other cases, and this includes buildings located in a flat open country, grasslands, and all water surfaces in hurricane-prone regions, e.g. a building in the middle of a cornfield, edge of town, or on the Gulf and or Atlantic shoreline. And actually that is D, that is not C. Okay, so for One Southdale, what is our exposure category? Credit if you say B, right? So it's actually built on the corner of a large shopping mall. And a lot of people have asked, well, it's kind of a flat surface. And not really, it's mostly a residential area and it isn't flat, it is broken up by these buildings. So we've determined that it is B. So write down exposure category B at the top in your worksheet. So now for topographic factor. So what is topographic factor? What that is the building on a hill, an escarpment, which is, it's just like in Billings, Montana, butte, and then, or flat ground. So if it's on a butte or this hill, or if it's flat, this is just showing you how they're determining how that speed works. And as it's going upwind, you see it speeds up. So it can affect how it affects wind pressure and how it hits the building. So typically it's going to be 1. I had one building in Billings, Montana. It was built on the side of a butte that we did have something other than 1, but 99% it's going to be 1. Okay, so step 3, topographic factor on your worksheet, we're going to put 1. Okay, and once again, that's just taken into consideration on the area and how it's affecting wind. So now this PNet 30 is, we're just going to figure out determining the wind pressure now. So as wind hits a building, a lot of people think that it's going to blow the windows in, which it can. But really what happens is when you see tornadoes or hurricanes on the TV and you see these buildings blowing up, what do you see? You usually see the roofs coming off the top, right? Or you see the walls blowing out. You'll see windows blowing out. They're not getting blown in. That's because of negative pressure. So negative pressure actually is stronger than the positive pressure. So that makes a big difference. Also, when it hits the building, so looking at this front elevation here, it's going to torque around these corners, and that's going to increase the wind speed and the wind load on the corners. So there's a special area, wind zone 5 that we call that. So in zone 4, and that's going to be 10% of the building. So when we look at our building and how the wind hits this building and affects positive and negative pressure, that's going into our calculation. So we have zone 4 is most of the elevation, but then you have 5% on the left and 5% on the right. And then as you wrap around the corner, that's another 5%. So we just call that 10% of the whole elevation. And that's important because I'm going to show you why. So we're going to calculate, and once again, this gets a little bit into the weeds, but it's pretty simple to just think of it as being 10% of the least horizontal dimension. You get into 40% of the height of the building, you know, but not less than 4%, blah, blah, blah. As the rule of thumb, just think of that 10%. So here we're looking at 10% of the 66 feet. So 10%, well, I rounded up to 67. We're at 6.7 feet. If you did take that 40% of the 33 feet, we get 13.2 feet. So once again, it just gets a little bit too complicated. We're fine at that 10%. Okay, so that is going to be 6.7 feet on either side on that corner. So then we just change that into 6 feet 8 inches. And what's important to remember here is any window or door that touches that zone 5, that in that 6 feet 8 inch area, that's going to have some special considerations to take into, because as that wind hits the building and then wraps around the corners, there's really more negative pressure that's going on in those corners. So I'm sorry about this slide here. I'm going to really narrow this down. So we have here on the left our zone 4 and zone 5. And then also the next column, you can take the actual area of the window and the door too. So they look at it being 10 square feet, 20, 50, 100, and 500. And what's interesting to note, just looking at this column, so this is the different pressures going on here. You see in zone 4 at 10 square feet, it's 23.8. And then you go up to 500 square feet and you're at 17.7. So actually the larger the area of the window, the less pressure is on that window. And so at first it doesn't seem logical, but think about, you know, a small window, a larger window, and even a larger window, and then just blasting wind at that opening. On the smaller opening, it's really acting like a tunnel, right? So it's just increasing that pressure. So that's why the smaller the opening, the higher the pressure. So we're just going to use 10 square feet here just for simplicity's sake. And then we're going to use that 115 mile an hour wind speed that we talked about before. We have our positive pressure and our negative pressure. And then here we have zone 4, which is 90% of the elevation, zone 5, which is that 10%. And now we're getting our design pressures. So we have 2 different design pressures. You can see negatively, it's really affected. Interestingly, positive stays about the same. But as I mentioned, that negative pressure is really what causes the damage. And so in our zone 4, most of the elevation, we're at a negative 25.8. And then the zone 5, the corners, we're at 31.9. And then when we deal with these wind pressures, we're always going to round up to the next 0 or 5. So in this instance, with 23.8, we're going to go to 25. And let's say in this 31.9, I'm going to go to negative 35 on that. So it doesn't get that, you know, that exact. So we're always going to go 20, 25, 30, 35, 40, like that, okay? Is it all making sense? Anybody have any questions right now? Okay. All right, so now we've determined our design pressures, our PNet 30. So we had our zone 4, positive and negative, and our zone 5, positive and negative. So if you're following along on your worksheet, put in those 4 numbers. So now we're going to deal with an adjustment factor. All right, So what is the adjustment factor? So we've determined the height of the building is 33 feet for our building C. So if we have our exposure B, we're going from 33 feet, we're rounding up to 35, and we have a chart. So for that, that's 1.05. And then you can see as your exposure goes to C and D, that is increasing that adjustment factor, which really can impact the performance. So where we're at, it's nothing too major, but you start getting up into that C and D, you can see how it really impacts it. So this is our lambda now. So our adjustment factor, or the Greek lambda, so put in 1.05. All right, so now we're going to finally get to our design pressure. So all this stuff that we've looked at, step 1, 2, 3, 4, and 5, we're finally going to get what we need to meet for our building. So there's our lambda. We have 1.05 from up here. Our topographic factor was 1. Our PNet 30 was our different positive and negative pressures. And then we also have our exposure category down here and all this other stuff now. So we're getting there. So you can see here, this is our design pressures here in the upper right, zone 4, zone 5. So now here, I was talking earlier about this deduction. So this is some interesting things are going on in the industry right now, and it's a pretty good debate between engineering, architecture, the window manufacturer, and what's going on with the building, especially where it's at. We can take a 0.6 deduction, okay? So what that does is when you're looking at this ultimate strength, that's what we figured out. Here's the 23.8 and the 25.8 for zones 4 and 5 and 31.9 in zone 5 over here. We can times that by a 0.6 deduction. So that really knocks us down below 20, which is like the minimum you're going to get. That was that R performance class. So I've talked to engineers and architects who say, you know, we're not going to deal with that. We're staying with that ultimate strength design, and that's up to you guys in the project. Just note that this is allowable under IBC code. So what this means, now we're at on our 33-foot high building. It's not really going to significantly impact that performance requirement, but as you get taller, it can impact going from a CW window to an AW window, which impacts the price. And by no means am I comparing performance to price when it comes to these complex projects, but somewhere in there is a happy medium where you can meet the performance and save some money if you are on budget. So it gets tricky, and I have to be very careful how I talk about it, because I don't want to go out and say, yep, you can do this 0.6 deduction and save all kinds of money on the project. It makes a difference on where and how big the project is. But this is something that's worth taking a look at. We run into it on a weekly basis. So this is just showing you multiplying 0.6, and now we have this 14.3, and then a negative 15.5, and then zone 5, we're at 14.3, and a negative 19.1. So the biggest difference here is zone 5. We're going from a 35 to a 20. And then this is just showing you the difference. This is the big thing that happened between 2009 and 2012 IBC. They increased the wind speed, but they allowed for this deduction. So now we're going to throw all this out that we determined, and now we use these newest figures for our PNet, for our design pressure. So you see it really lowered the bar. All right, so now we have our design pressure. We're going to need to calculate water performance, okay? And that's going to be based on AMA 101. So how do we do that? So we need our DP, and we're going to times that by a 0.15. Okay, so our DP, 14.28. So I'll go back here. So we're using this one, our zone 4 and zone 5 positive pressure. Times 0.15, and we get 2.1 PSF. That's hardly anything, right? So we have a minimum water test pressure of 2.86. So even though we calculated underneath, see, that's what I'm saying, you know, we really are, with that deduction, we're really into this. Anybody can make a window, basically, that can meet this performance. So they have come up with a minimum water test pressure of 2.86. And that means that no water leakage at 2.86 pounds per square foot. And that's the equivalent of 8 inches of rain per hour at 30 miles per hour. So for those of you that have witnessed the water test, what they do is they'll put up spray nozzles on the exterior of the building. They'll put up plastic and tape it up on the inside, and then hook up the vacuum like you're seeing in the lower right here into a hole, and then they're going to suck the air through. So it's negative pressure, and if there's any water that's coming in, you know, because of the window installation or at the malls, we've seen water coming in, we're gonna see that. And it's a good test for these large, especially multifamily. We see it a lot. It's better to test the windows out and the installation before they start putting in all the windows. You just want to make sure everything is right. So we're all about specifying water tests. Okay, so now getting back to our worksheet. So we have all of that stuff. Now we've figured out our water test pressure. So that's what came up here. So our 0.15 times the 14.28, we determined it to be 2.1, but we have to meet the minimum of 2.86. Oh, I just see a spelling error right there. Okay, so 2.86 for water test pressure. So now, how are we going to put this all into specifying air, water, and structural performance? All right. So looking at our friendly spec here, window performance requirements, we come down into our performance class and grade. So we talked about R, LC, CW, AW if needed, and then our minimum performance grade. All right, so what we're going to do now, here's how we get the performance grade. So we have our negative 15.5, our negative 19.1. I'm always looking at the negative numbers because these are always going to be larger than the positive numbers. So it's just instinctive for me to go to those negative numbers because those are always going to be the ones that we need to hit. Like I said, you always round up to 20, and then in this case, it'd be 22. Well, 20. All right, so performance grade of 20. Okay, everybody understand that? Hope so. Performance class. All right, that's going to be up here, and really, it's a light commercial building. So here's how we're going to look at this, though. And once again, this is a pretty complicated slide, but I'm just going to take this old stuff right out. They're going to build up the slide here. Here's where it was back in 1997. Like I said, there was 5 of them. And you can see it was based on air infiltration, minimum water test pressure, and then minimum design pressure. And you can see it's nothing too major until you start getting up into the heavy commercial and the AW. So then it all changed. about 10 years ago. So now, here we are at R. So residential, 2.93, 15.1 minimum design pressure. AW, once again, that's where you're getting a significant bump. So that's what we're always looking at. R, LC, CW, most window manufacturers make these windows. AW, we make AW windows, but you're getting into a really higher performing window at AW. So R, and back in one of my earliest slides, I talked about these minimum gateway requirements that go into R, LC, CW, and AW. And I still call it residential, light commercial, commercial, and architect. But here's what they really want you to consider it. So R, commonly used in 1 and 2 family dwellings. LC, low-rise, mid-rise, and other buildings for larger sizes and higher loading requirements are expected. CW, just even higher requirements, limits on deflection, heavy use. And then AW, high-rise to mid-rise, but really increased loading requirements, deflection, and extreme use of fenestration products. So, as I said, there's no code, there's no standard with this. This is just some basic thinking about that performance class. Now, as I said, there is minimum testing that goes into this, so it's not something that just needs to be dismissed. But we see a lot of times, where spec writers and architects are specifying CW windows where LC can be used. So that's fine, but sometimes you're over specifying. And we see AW being specified where you can use LC or CW, and that's fine, but a lot of times that impacts the cost. And once again, cost matters in a lot of these projects. And I don't want to get into the really complex projects. I'm not trying to say if AW window is not required. AW is the most important window for these complex projects. But if it's LC or CW and we see an AW window spec, we're going to call you and just talk it through on really what we're dealing with and see if you'll accept, a LC or CW window. So it does impact price. Okay. So now this gets, once again, kind of a complex slide. Basically what we're looking at is this is all the testing that goes into performance grade. And then it's based on these different types of windows. So here we just have 4: awnings, casements, fixed windows, and hungs. There's actually 34 types of windows. So we're just breaking out 4 types of windows between performance classes. And this just gives you a look on how this breaks down. So here we have the casements highlighted. So minimum performance grade, I've talked about that at length. I hope that makes sense. Here's that gateway minimum test size. All right, then we're talking about our minimum water test pressure. So we were dealing with 2.86 before. And once again, just really look at the differences, see an allowable air leakage here. Nothing changes from R to LC to CW, but it really goes down with AW. So this is where you're getting great performance, but sometimes you're paying for it too. And then there's other things as max operating force, max lock force, max deflection. There's sash leaf torsion that I have a slide just to show you what they're doing there. They're just measuring that deflection for the leaf torsion test. So a lot of people don't get this deep, but if you need to know, we test all these windows. Every manufacturer has to do these tests. So sash vertical deflection test. There's casement hardware. And then once again, just looking at AW here, they have a life cycle test too that AW is considered for. So that's the important thing, is AEW is just at its own level here. Casement hardware load tests. This is just all these testings here. Okay, so we're getting down to the nitty gritty. Thanks for hanging with me. Hopefully this is starting to make more sense. For our final performance class, right, we're going to determine that R through that CW is going to make the grade, right? Once again, AW is just a little bit more than what we need. And then just looking at this for either further going up the chain, there's product and design options that we can always look at too. So for casements, the hardware going up to a performance grade of 50. So that's inoperable. In fixed frames, pretty easy to get really high performance. If you do need some increased performance in some of these projects, if you stick with a fixed frame, you can go up to PG 90, relatively easy. And then, as most of us are aware, on outswing patio doors and talking about water resistance, here we have a standard sill up to a DP 70, water resistance at 10.66, pretty good water resistance. We go down to that ADA sill, we have the DP 70, but there's no water resistance, right? That sill, you can see there's just no gasketing, no real blocking of water coming in. So as most of us know, this is kind of the holy grail right now. You know, as our company's looking at options to get some kind of thing in here to help water resistance. So now getting back to our worksheets, now we've figured out our test pressure, our performance class, R through CW, and our performance grade of 20 to 30. So we figured out we were at 20, but they're going up to 30 just for that increased performance. So now, if you remember that blank worksheet that was blank, we've worked through all this. So I know there's probably some questions, probably some clarification. I'm open to hear your comments, concerns, complaints. Anyone? Would love to hear some feedback.
George, I have a confession to make, and that is that I feel really dumb or really old. What happened to the HC window, which was sort of our go-to back in the day when I was writing specs?
Yep, and that was that 10 years ago where I don't know, George, what really changed everything to go to that, but yeah, they went from the 5 performance classes to 4, and they took that HC window out. And as far as an explanation, I don't have an answer for you. I can talk to one of our code guys who he's been with Pella for 25 years. I'm sure he can answer that for you. I can shoot you an email.
And sort of the follow-up to that with the 4 classes now, is there visually any difference among them? Because now we're maybe having to mix different classes where, you know, years ago you didn't do that.
Right.
So if you have one right next to the other, will you visually tell the difference?
That's a great question. So depending on what material you're using, so like an AW window, you know, the highest performing window I've seen, you know, it's an AW 100, something 110, which is a pretty beefy aluminum window that's, you know, a pretty thick, deep frame, and it can just withstand, you know, being put into the Empire State Building, you know, and you are going to notice a difference. Just the frame is going to be beefier. They're going to have thicker glazing. Yeah, another thing that you can look at is vinyl windows are just coming on stronger. There's some really cheap vinyl windows out there, as we're all aware of, and they're going to have just a lot of plastic involved because structurally they don't have much in there. So there's a lot of these local vinyl companies that are building R20 windows, but you see, and they're going to be thick windows too, where a material like fiberglass, it's going to be a lot stronger and a lot thinner when it comes to the frames and the molds. And so that's another good point too, is not only the look of the windows themselves, the frames, but the mulling too. When it comes to design pressure, you have to have the molds that also meet the requirements. So with vinyl windows, because they do lack that structure, we see a lot of 6 or 8 inch wide mulls because they have a lot of steel or wood in there, where aluminum and fiberglass and even wood clad is strong enough where you can get away with a 4-inch mull. So there is a lot going on there, and our company will do preliminary drawings for you just to show you the differences. But it really is based on the different materials. So good question. It does make a difference.
Yeah, that's one of the nice things about performance spec'ing, is that it covers basically every material that you could think of that a window's
Yeah.
made of. But the downside, like you mentioned, is that once you've got the performance, then you need to get into these other things about what's the most appropriate material to be used.
Absolutely. Correct.
I have a question.
Yeah.
Oh, here's a video. Unable to start video. Oh, okay. Well, whatever. That I don't practice anymore, so this is just hypothetical. You've got a corner window that's withstands greater pressure than in the middle of the elevation. Do you ever see on jobs where they don't they mix up the spec, and so they don't put the right window in the right place?
I have seen that. I've seen everything from, tempered windows going where they're not supposed to go. But then if you're specifying different performance
Sure.
levels.
Yeah, that's what I'm saying. You got the corner and you have the mid elevation.
Yeah, so that has to be clearly marked by the window manufacturer. Because yeah, it's happened for sure. And then, I was going to show you guys, and I apologize, with all that we went through, here's an easy calculator. So we had, just to show you how, and this is what Steve and I do on a lot of these projects. So you put in what state it was, it automatically gives you that ASC 7. We were at 33 feet. Our risk category 2, design at 115. So you can see this automatically calculated. So this is what I wanted to show. Instead of going longhand, I just wanted to show you the concepts and how that's developed. But you need all that information. So you put that information in, you hit enter, and here you get this pressure. And like I said, I want to bump this up because 33 feet is just not doing it justice. So let's go to 133 feet. So now you're seeing a dramatic difference in what's needed here. And like I said, these negative pressures are always going to be a lot higher than the positive pressures. So right here, my eye is just drawn up here because this is where the highest requirement is. So here for a 10 square foot opening, we need a PG 40, and at 20 square feet, a PG 40. Here we have to go to PG 45 if it's 50 square feet. And then, I've never used the 500 square foot opening, but you can just see how dramatic that difference is. So this is always the big one here. I wish I would have shown that soon. I hope not everybody dropped off, because this is what we use a lot. So instead of going long-handed, this is where the engineers have it made in the shade because they have all these calculators and look really smart.
Is that a Pella product, or is that something you get elsewhere?
Excellent question. I think that's George. This is a proprietary calculator, and then we use it for molds too. So we can put in additional information based on height and width to get different mulling options, because as I said, that's an important part of it too. And Steve or I can do these calculations. Just, basic ones. I never do anything on behalf of an engineer. If you guys just need some basic information, we're happy to do this, but I will always submit for an official design analysis, we call it, that's done free of charge. And that is done by one of our engineers and is signed off on, where the architect or spec writer can take that to your structural engineer and just make sure we're all on the same page. And if we're not, it always comes to a conversation on, okay, what are we missing? What are we doing differently? Does this impact, how does it impact performance, and how does it impact cost? All right. Well, that's 7 o'clock. I appreciate it. If there's any other questions, feel free to shoot an email to George, or Steve Bowles is the local rep in St. Louis. He's an awesome guy, and he's been in the business for 25 years, long-term Pella employee, and a great commercial, knowledgeable rep. Just email Steve any questions, or he'll send them to me, and we'll be glad to help you guys out on any project. So thank you.
All right, George. Well, I think hopefully we didn't lose Derek, and he's off the ceiling now, because he was pretty anxious when he
I
saw
am
some
still
of those.
shaking. I am still shaking. So, but I feel better.
Okay. So some of this is just, picking the right column and knowing what each column stands for, and
Right.
just kind of pick and go from there. So I think that's good. And I think the other thing, as you said, and we all appreciate, is when in doubt, we can give you a call, and you can,
Exactly.
help walk us through some of this as we need.
Absolutely.
But
Joe,
George-
one of the
yeah.
things that strikes me about this is those of us in our age group recall what it was like taking our architectural test and learning about seismic, right? And we had basically a 6-factor thing we had to learn. And as our careers developed, they learned more about earthquakes, and that factor changed, the maps changed. And it strikes me that with windows, it's basically the same thing. I mean, obviously, this is the result of decades of experience, probably from failures and so forth. And
Well-
that's really cool. It's good to see that it continues to change for the better.
Yeah. Oh, and they continue to improve what's going on in the hurricane zones, especially.
Yeah.
There's constant conversations and improving standards.
Well, they've had some hard lessons, and they've learned, and they've been able to analyze more about what really happened, as opposed to, oh well, this blew down, and so now we know a little bit more about that.
Yeah, building science. That's where it's
Yes.
at.
Yep, it continues to get refined, and we get pressures from no, sorry, no pun intended, but we get we get things coming at us from multiple directions with trying to refine these, and so okay, once again, George, thank you very much. Very interesting. Hopefully everybody got some enlightenment out of this. If nothing else, we now have a couple of good names to go talk to if we have questions. So once again, if you need certificates, if you need AIA, please pass your information, AIA membership number, if that's what you're looking for. Certificates, just pass on email in through the chat boxes, so we can gather that up and get all that reported.
And one more thing, we've been recording the video and the audio of the presentation. We'll put a link to it on our website. We have a YouTube channel also, so we'll get that done probably within the next couple of weeks. And George, would it be possible for me to get a copy either by PDF or of the presentation? I could put that also.
Yeah, no problem.
Okay, just send that to me and we'll get that done.
So even better. So if you just said, what did he say here? You know, we'll have that up there here before too long too. So that works. We will have a presentation in January. The next presentation is an economic forecast by Lynn Tones from the AGC. I think it's always been interesting. It promises to be even more so this year. We'll see what kind of things he pulls out of his crystal ball here. I want to wish everybody a very happy and safe holiday season. Everybody stay safe, stay healthy, and be good out there. So thanks, everybody.
Thanks, guys.
Thanks a lot.
Hey, Joel, just to confirm, that's January 20th, right?
Shoot, I did not have that in front
It's
of me.
okay.
at the
It's
time.
okay. No worries. No worries. I got it blocked out. Figured the notifications will come out. Thanks, George. That was great.
Yep.
Thank you.
Yep.
In spite of the math, it was great.
January 20th.
Yes. Thank
Perfect.
you.
All right.
Yes. Okay,
Good night,
everyone.
everybody.
Good night. Thanks.
Bye. Thank you.